Let's talk next about drug distribution. Where does the drug go? Well, we said first we want to have it in the circulation. We're going to measure it in plasma, but it may not stay in the plasma. Based on the chemical properties of the drug, it may distribute further. Where else could it go? Well, first it could distribute in total body water. So if the drug can pass the endothelial layer here of our blood vessels, what else is there? Well, then there's the interstitial fluid. It would get into the interstitial fluid. Well, maybe it can even get into cells. If it passes the lipid bilayer, the plasma membrane, it could even get into cells. And if it goes anywhere here into plasma and distributes into interstitial fluid and intracellular fluid, that would mean that it's going to distribute in total body water, because that's our total body water. So in order to understand where the drug went, if we want to figure out where did it go, how much do we need to get a certain effect, we need to understand, we need to have some numbers in our mind as it relates to total body water. So what we know is that our total body water is 60% of our weight, so 0.6 times weight. Where is our total body water? Well, in the plasma, that's one thing. Plasma. Then we have the interstitial fluid. And then we have the intracellular fluid. And the intracellular fluid, we can say this is intracellular, and we can summarize plasma and interstitial as extracellular fluid. Or we can also call it extracellular water and intracellular water. It means the same thing. Now, if this is 0.6 of our body weight, so 60%, well, what we know is that the extracellular is 0.2 of our body weight, so 20%, and the intracellular is 0.4, so 40%. And then if you want to also split this up, so the plasma is 5%, so that's 0.5 our body weight, and the interstitial is 15 body weight. Okay, so let's follow the drug and let's think about a key parameter that determines the distribution, which is the volume of distribution. And the volume of distribution is defined as the dose per kilogram weight divided by the plasma concentration. So that's what we measure here in the plasma, CP, plasma concentration. And you're gonna have to be able to interpret a volume of distribution of the drug and figure out what does it mean, where did the drug go? Okay, so I'm gonna give you now a couple of examples. So let's suppose the volume of distribution of a drug is 0.05 liters per kilogram. What does that mean? That would mean that the drug has just distributed into the plasma, has just got into the plasma and didn't make it into any other body water. So the volume of distribution is very small, which makes sense because you measure the concentration of the drug in plasma. So that's going to be very high if it's just got into the plasma and didn't go further. Then this is a very high number, which means the volume of distribution is going to be low because you have a high number in the denominator. Let's try this with a different volume of distribution. Let's suppose the drug got into the interstitial fluid. So it was distributed, it was here, And then it also got here, so we have distribution between plasma and interstitial fluid. What do you think is going to happen to the volume of distribution? Well, let's look at this formula. So Cp is a plasma concentration. So this is going to be, if it distributes also in the interstellar fluid, it's going to be lower in the plasma because it's always in equilibrium. So this is going to be lower, so therefore the volume of distribution goes up. And here we would expect a volume of distribution around 2 liters, 0.2 liters per kilogram, because now we made it into the extracellular fluid. Now let's suppose this drug also passed this plasma membranes and it got into cells. And it's gonna also distribute intracellularly, so into intracellular fluid or intracellular water. Then we would expect a volume of distribution of 0.6 liters per kilogram, because now we are in total body water. Now, let's imagine you're dealing with a drug that has a VD of 2.2 liters per kilogram. Now you may say, wait a second, now my volume of distribution is bigger than actually all my body water because I have only 0.6 liters per kilogram. Well, what does it mean? That means the drug also went to other places and distributed in non-water tissues, such as fat. So let's put in here a couple of fat droplets. So let's suppose that's fat or any other non-water sites. Could be bone or any proteins inside cells. So just somewhere else. If you have a very high volume of distribution, meaning it's even higher than the total body water, then you know it has sequestered somewhere else. Does that make sense with our volume of distribution formula? Sure, because now we say, well, the volume of distribution is large, so that means for a given dose, the plasma concentration is going to be low because it's all in equilibrium, so it's going to be very low here to measure in the plasma concentration of the drug. Let me just add here a couple more details about the volume of distribution. First, I want to add that this is a fictitious volume because, as we already said, there cannot be anything larger than 0.6 liters per kilogram. That's all our body water. That's all our volume we have. So it's fictitious because once it gets larger, it just means it's somewhere else, but it's not a real volume. And then another thing that I want to add is that actually to get the volume of distribution, you need the plasma concentration at 0.0, so immediately. Why? Because once elimination kicks in, things get more complicated, and then you couldn't really determine your volume of distribution anymore. So really, if you want to think about it as a simple model, it just means how, if you have the volume of distribution, how big is your bucket? You're going to add a certain dose of a drug into this bucket that's going to give you a certain concentration at the time 0.0 before we can say the bucket doesn't have a hole yet. So elimination is not yet going on. That's kind of the volume of distribution. And how you can easily remember this formula, well, I think everybody knows concentration is mass divided by volume. So you just solve it for the volume, and then you have the mass, which is a dose, divided by the concentration. In that case, kind of the immediate concentration before elimination kicks in.